Hello and welcome to Physical Attraction. Despite the impending and inevitable heat death of the universe and everything falling into the ultimate pit of chaos and entropy, we defiantly and disgracefully remain the show that tries to explain physics however we can. In this episode, we're dealing with the third law of thermodynamics, so if you don't like spoilers, you might want to go back and listen to the first two episodes about the first and second law. Usually I do try to make these episodes so that you don't need to listen to anything else to understand them, so that they're standalone. But here I think at least the episode on the first law will be helpful, because that's where we defined what absolute temperature was. You'll need this for today's episode, and it will probably really help if you know about the second law as well. I will quickly recap, but I don't want to bore the dedicated hardcore fans who listen to every episode. So if it's confusing or you're a thermodynamics novice, listening back to the first few episodes of the thermodynamics series might really help. So today's episode, the third law. So far we've dealt with the first two laws of thermodynamics. The first one says that you can't win. Energy is always conserved. You can't produce energy from nothing. The second one says that you can't break even. All processes involve entropy, disorder, increasing, and losses to heat, which is like the disordered motion of atoms. So whenever you use an engine to do work, and more broadly in any process where energy flows, some will be lost. You pay an energy penalty. You can't break even. Now the third law of thermodynamics says that you can't get out of the game. As if the game wasn't rigged enough. But what does this mean? Essentially, the third law of thermodynamics says that you can't cool anything down to the absolute zero of temperature. Nothing can be cooled down to absolute zero, at least not in a finite amount of time. So we've already discussed that the temperature is a measurement of, broadly, how much energy molecules have. The higher the temperature, the more kinetic movement energy the molecules have, the faster they're vibrating around, if you like. Zero on the absolute temperature scale implies that the molecules have no kinetic energy at all. They're completely still. But you can never reach this. It's impossible. As far as temperature goes, you can't get out of the game. And you can see this by the second law of thermodynamics in a lot of ways. Remember we were talking about the Carnot efficiency, this idealized efficiency of a perfect engine? The most efficient you can be when you're converting between forms of energy, when you're trying to change heat into work, is the Carnot efficiency, and this is 1 minus T sink over T source. So this is for a heat engine that converts heat into work. But if you run this heat engine in reverse and convert work into moving heat energy, then the efficiency becomes T cold divided by surroundings minus T cold. So that is to say, as the cold temperature approaches zero, the efficiency of something that converts work into moving heat energy around approaches zero. In other words, you can put in an infinite amount of work without driving any more heat away from the cold place. In a bizarre but very, very real twist of the laws of physics, you need infinite energy to get anything down to zero energy. And you can sort of see how it might become more difficult to get down to zero energy altogether, right? Because heat always flows from hot to cold, you'll always have a hotter region surrounding your cold region that you're trying to freeze. It will be very difficult to stop that region from passing any energy towards the colder region. But this isn't just a practical problem that it's difficult to perfectly insulate. It's just that the colder something gets, the harder and harder it is to pump more heat out of it. Eventually it becomes almost completely impossible. This can also be defined in terms of the entropy of the substance that you're trying to cool. So it's helpful to remember the definition of entropy in terms of a kind of disorder, or alternatively, how many different microstates there are that correspond to the same overall thermodynamic macrostate. Remember that a microstate is like the specific arrangement of the atoms that make up your substance, while a macrostate is the bulk properties of the system, like temperature, pressure, and so on. It's a little bit like fans filling up a stadium. If the stadium is half full, there are plenty of different ways to arrange the fans to keep it half full. Plenty of microstates that correspond to that macrostate. If the stadium is completely full, or completely empty, however, there's only one way to arrange those zero fans. Maybe it's a Nickelback concert? So this would be a very low entropy system. So there's some entropy associated with the temperature of the system. And this you can sort of see makes a lot of sense, because the system has thermal energy due to its temperature, so there's more possible energies that the molecules can have. The molecules have a bigger range of velocities and momenta that are feasibly accessible to them. Obviously, the amount of energy you have puts a cap on that. You can't have one particle moving with more energy than the whole system. But even when the molecules have no thermal energy at all, there can still be entropy due to the arrangement of the molecules. If a perfect substance has a perfect crystal, such that there's only one possible position for all of the molecules, then at perfect zero, at absolute zero, it has zero entropy. But such a perfect crystal doesn't exist. Why does this mean that absolute zero can't be attained? To understand this, we need to know a little bit more about thermodynamics and state functions. So a state function sounds complicated, but essentially it's just a function of the variables that define an individual macrostate. So we've talked about these macrostates as being things where you specify state variables like temperature, pressure, etc. And a state function is something that is a function of one or more of these variables of state. So you can have things like entropy as one, enthalpy as well, the Gibbs function, and the Helmholtz free energy. And defining these functions is very useful because they correspond to different processes in thermodynamics. Sometimes you can say that the Gibbs free energy is conserved, and by looking at that you can see how the system will evolve and behave in the future. But basically, cooling processes usually work as follows. You're flipping between two states for the system. One flipping process reduces entropy at constant temperature, and one reduces temperature at constant entropy. So you can imagine it like the steps of an escalator stepping down between the two graphs. One is the function entropy of temperature for one state, and one is the entropy temperature function for another. And you go down on the graph where you're reducing entropy at constant temperature, so that's vertically down on the graph. And then you also go horizontally along on the graph where you're reducing temperature while entropy remains the same. So one way you might imagine doing this, it's very popular, is by changing the magnetic field. This is a process called adiabatic demagnetization. So you switch between the two curves by changing the magnetic field, turning it on and off again. And then, in the meantime, you cool. Another way you might do this is by allowing your gas to expand into different chambers. The volume change then is what causes the change in temperature or entropy. But basically, whatever you're doing, you're twiddling the system so that some of the entropy that used to be associated with temperature is now associated with something else, pushing the temperature down. Then you remove entropy by setting your dial back to zero again. It's a cyclical process that reduces temperature and entropy in stages. Obviously this requires energy to do, but that doesn't matter. We're assuming that you can shove the temperature and you can shove the entropy somewhere else for now. But regardless of your state, if you have the same entropy at absolute zero, you have a problem. That escalator will need to have an infinite number of steps. Imagine two curves that intersect on the axis, and you'll see that you actually can't draw a finite number of steps that get you down to that intersection point. I'll put in a graph to the show notes to make this a bit clearer. But because we know that entropy tends to a constant value, which is only zero for a perfect crystal at zero temperature, and we know this because then the only entropy that exists is because of the possible arrangements of molecules in the crystal lattice. And because of this, we know that in fact the graphs do intersect on the axis, and therefore no process can get to absolute zero in a finite number of steps. Which means that if you want to get to absolute zero, it will take infinitely long, and since each time you do a step on this graph, it involves some transaction of energy, it will also cost you an infinite amount of energy. Despite this though, providing you're willing to go through a lot of steps, you can get down to some incredibly low temperatures. 2.73 Kelvin. That's the temperature of the background radiation of the universe. If you go out into the vast wastes of outer space, there's something called the cosmic microwave background radiation. It's going to be a great episode when we get to it. But essentially this is relic radiation from the Big Bang. And that is the only thing that sets the temperature of the void between stars and galaxies, this radiation bouncing around. But we can actually get to colder than that on Earth. We can cool to well below the temperature of this empty void. By the way, it should be clear to all of you who've been listening so far that you really can't cheat thermodynamics. So of course, whenever we cool anything down, the second law is still not violated. Entropy still increases. So when before, in our adiabatic demagnetization cooling process, we were pushing entropy away from that system so that we could then reduce the temperature again, well, what's happening is we're actually pushing that entropy away, and we're giving the outside world even more entropy than the system has lost, because any process in an isolated system must increase the entropy. And in fact, more heat is also produced, which makes sense. You can imagine it in simple terms, really. You need to do work to drive heat from a cold place to a hotter place, according to the second law. Some of that work will be wasted as heat, because always some work is wasted as heat. So the total amount of heat that's produced is the waste heat from the work and the heat that's driven away from the cold place. Your fridge freezer pumps out plenty of heat at the back, more than it takes away from the stuff inside. And there's no way around this. And similarly, if you're listening to me and neurons are making connections in your brain that's perhaps hopefully becoming less disordered and containing more information, this process too also means that entropy will increase somewhere else by a greater amount. Any of you who've looked at yourselves in the infrared will know that actually you lose a lot of heat through your head. You can't cheat thermodynamics. We already talked about adiabatic demagnetization as a popular method of cooling. There are also more refined and specialized methods. One of them, which, yes, sounds very cool, is laser cooling. It might seem counterintuitive to imagine that zapping atoms in a gas with lasers can be used to cool them down, but it's true. We normally think of lasers setting things on fire, but in this case you can use it very cleverly. So here's what happens on the atomic level. Usually the atoms are trapped down by some clever method, probably using electric or magnetic fields, so they can't escape. Imagine James Bond being pinned down and strapped to the laser table, if you like. Scorpio, you're totally mad. The scientists then zap an individual atom with an individual laser photon. The photon is then re-emitted by the atom in a different direction. It's a familiar process in physics. So far, so good. But what actually happens is that the photon is re-emitted with a slightly shorter wavelength than before. This can happen due to something called the Stark shift, for example. The electric field of the photon itself actually distorts the energy levels of the atom, making them split wider apart. So as the photon is being absorbed by the atom, the energy levels are being distorted. And so it's absorbing a slightly more energetic photon than it then re-emits. And alternatively, this can happen due to Doppler shifts. So the Doppler shift is familiar to anyone who's ever heard a car rushing by. As the car approaches you, the relative movement between you and the car squishes the wavelength of its sound wave so that it sounds higher pitched. It's got a shorter wavelength, so it's got a higher frequency. As it moves away from you, that wavelength is stretched, so the pitch gets lower, which is how you get your The same can happen when an atom in a gas has some velocity in some direction. The Doppler shift means that it can absorb a slightly longer wavelength photon and then emit one with a slightly shorter wavelength. In other words, it's emitting a photon with more energy than it's absorbing. Now we all know that energy is always conserved, so that extra energy in the emitted photon actually comes from the kinetic energy of the atom. That means that it slows down and it cools down because it has less kinetic energy, it's got less temperature. Using incredibly precise techniques like this, researchers have been able to cool things down to temperatures of a billionth of a Kelvin. Remember that 0 Kelvin is unreachable, absolute zero, and that actually you need more and more energy to cool things down when you get to these lower temperatures. The background temperature of the universe itself, empty space itself, is 2.73 kelvins because of this cosmic microwave background radiation. So we've cooled things down to billions of times cooler than empty space. So this is almost as cold as you can imagine going. Or is it? Occasionally you get reports in the news which can be quite misleading that they've attained negative absolute temperatures. This is always a little bit of a fudge though, because it depends what measurement of temperature you use. When they talk about negative temperatures, they don't actually mean that the area is colder than absolute zero. That would imply that then if you put something at absolute zero next to it, heat would flow from your absolute zero into your negative temperature zone, right? In actual fact, the areas that they say have negative temperature are warmer. Confusing, right? That's why you need to read past clickbaity headlines from time to time. because it's not always what you think. So let's try and understand why they call this a negative temperature, and why it kind of makes sense. One way of understanding this is by imagining a set of 100 atoms with two possible energy states. So you can imagine two levels in your head, if you like. The atoms can be on level 1, or they can be on level 2. This means that all the atoms are in either one of the two energy levels. Now remember what we learned about entropy. It's how disordered a system is, how many microstates correspond to the macrostate. And temperature is linked to entropy, intricately. In fact, by one definition of temperature, it's how much energy you need to change the entropy by a certain amount. If all the atoms are in the lowest energy level, that's about as ordered as your system can get. You've got very, very low entropy. In fact, entropy is 0 in this case, if there's only one way of arranging the atoms so they're all in the lowest energy state. But if you give the system a tiny bit of energy, enough to kick one atom into the higher energy level, entropy will massively increase. After all, there are 100 ways of arranging things if 1 out of 100 atoms is in the higher energy level, because it could be any one of those identical atoms. So entropy has gone up by quite a lot, and it only took a tiny amount of energy to do it. So this is one definition of low temperature. The amount of energy we need to change the entropy is low. And you can see that it actually makes sense, right, for us to say this is a low temperature system. All the atoms are in the lowest energy state. That sounds like a low temperature to me. And then we kick up one of the atoms into the higher energy state. We've given it a bit of energy, the entropy has changed massively. The temperature must be low, because we required only a tiny bit of energy to change the entropy by a certain amount. But if you have this definition of the temperature, you can imagine a different scenario. So the maximum entropy scenario is half and half. Half of the atoms in one energy level and half in the other. This is kind of the most disordered way that the system can be, and it makes complete sense, right? Because if everything's in level 1, 0 entropy, completely ordered. If everything's in level 2, again, completely ordered, 0 entropy. So half and half is kind of the most disordered way the system can be. So now imagine that we do have half the atoms in the lower energy state and half in the higher one. Then we somehow prod the system, pushing atoms from the lower energy state up into the higher one. Now, we've given the system more energy because we've pushed atoms from a low state to a high state of energy. But the entropy has actually gone down. So, if the temperature is something like the change in entropy over the change in energy, the temperature is now negative, isn't it? Because we're putting energy into the system and entropy is going down. So what that means is literally that you need to remove energy from the system to increase the entropy back up to its maximum, the half and half state. So in a sense, in a sort of mathematical sense, the temperature is negative. But weirdly, it's because this region is actually more energetic than average, right? It has more atoms in the higher energy state than you would have in equilibrium to maximize entropy. Scientists have been able to create similar states to this by prodding these individual atoms in the low energy state, and sometimes this gets reported as negative temperatures. But it's not the same as saying, you have to put energy into the system to get up to 0 Kelvin. That's what you'd think with a negative number, right? It's something you have to add numbers to get it to be positive again. But that's not the case here. In fact, it's very different. If you put a negative temperature object next to a positive temperature object, the energy would flow from the negative temperature one, with higher energy, to the positive one. And you can see that it only works because of these weird quantum effects, right? We're limited in the energy levels that our atoms can possibly have. You couldn't have negative temperature for, say, molecules of a gas that are moving around, because you can always add more energy, and you can always increase the entropy. There's no maximum energy for their motion. Even when they're sort of approaching the speed of light, you can always add more energy and they can always go faster. It's only in certain types of quantum mechanical system, where stuff is limited in the energy levels it can occupy, that you can produce one of these negative temperatures. So really, we should say something like negative entropic temperature or negative quantum temperature, because otherwise I think it's quite misleading. Absolute zero remains this barrier, this unattainable zero of temperature. All this talk about negative temperature might have you thinking, okay, 0 temperature, 0 Kelvin is the coldest that anything can be. Is there a limit to how hot things can be? And the answer to that is, maybe. It might just be that temperature stops making sense at really high energies. Essentially, at really high energies, at really high temperatures, the laws of physics start to change. So one example people talk about when they talk about this idea of absolute hot, which, there's a chat-up line in there, right? But instead of absolute 0, maximum temperature is called absolute hot. One idea they talk about is the Planck temperature, which is around 10 to the 32 Kelvin, or 142 quintillion kelvins to be more precise. So this is a really strange concept. If anything ever reached the Planck temperature, gravity would be as strong as the other fundamental forces. Our current laws of physics just can't describe matter in this state. We have no idea how anything would happen at 10 to the 32 Kelvin. It's too hot. Hot damn. And yet we also believe that the universe, however briefly, perhaps 10 to the minus 42 seconds after the Big Bang, was in this temperature state. Things must have been very strange indeed there. And because we don't know, because this is unreachable, because heating the smallest volume of space to this kind of temperature would be the same as conditions immediately after the Big Bang, some have even speculated that it might be, in some strange sense, the same as absolute 0. Temperature is a circle. We need to change the shape of thermometers, that's pretty wild. But there are other answers for what the maximum temperature you might get can be. And again, it comes back to the rather shaky and many different definitions of temperature. So there's one that I quite liked, which actually only works for baryonic matter. It's called the Hagedorn temperature. I hope I'm saying that right. Beyond this, you can't reach hadrons anymore. So hadrons are the type of matter that are made out of these tiny subatomic quarks. And it turns out that if you heat them beyond a certain temperature, instead of getting hotter, they just start producing more hadrons. In other words, that energy that you're putting into the system to heat it up is only being converted into more particles, rather than heat energy in the particles that exist. In some sense, you've boiled the particles down into a soup of quarks, and when you add more energy, rather than heating the soup, you add more quarks to the soup, which produces these fireballs of new particles. So in a sense, the temperature of this kind of matter stays the same, no matter how much energy you put in, at least until something even wilder happens. The amazing thing is that we can actually reach the Hagedorn temperature at places like CERN in the Large Hadron Collider. Briefly, the hadrons there get so hot at any new energy you put in just goes into making more hadrons rather than changing the temperature. In a sense, temperature has maxed out, because, we can't heat anything anymore, so it doesn't make sense to talk about temperature. But there are other ways to measure it, say the entropy of the produced particles, that will show it continuing to go up. And if you look at something like the frequency of light as an example of the measurement of temperature for radiation, then you'll see that this Hagedorn temperature definition doesn't really apply there. So you'll probably remember from our episode on superconductors that the physics of matter at extremely low temperatures can get very interesting indeed. And this is basically because quantum effects are starting to become very important. For superconductors, for example, the electrical resistance suddenly drops to 0. You can pass currents through a coil of superconducting wire and they'll still be there, without losing energy, billions of years later. There are other fascinating properties of matter that emerge at low temperatures, including things like superfluids and other such exotic states of matter. And perhaps, by pushing matter closer and closer to absolute 0, we'll find more and more strange properties that can arise when these quantum effects start becoming important. Essentially, when you probe matter at these tiny temperatures, the fact that energy is quantized, that it exists in these little packets and it's not continuous, you can't have any value you like, becomes very important. This is because energy is basically temperature times a constant, and in fact it's Boltzmann's constant times temperature gives you energy. So the energies that you're dealing with at these very low temperatures are about the size of a quantum packet, rather than so many packets that it looks continuous, which is a big part of why so many strange properties start to arise. But more on this, I think, we'll have to wait for our big quantum episodes, and that is going to be a fun series to put together. So, there you have it. The laws of thermodynamics. Energy cannot be created or destroyed. In an isolated system, entropy will always increase. Absolute zero of temperature is unattainable. You can't win, you can't break even, and you can't get out of the game. These laws, discovered often by thinking about gases and idealised heat engines and so on, discovered centuries ago, have proved amazingly resilient over all new kinds of physics. We see that they are far more fundamental than the original scientists who came up with them may have thought that they were. On almost all theories, even really wild, exotic states of matter at strange, extreme conditions that we rarely find on Earth, they seem to be bound by these rules. Their consequences, the action of these laws, ranges from the motion of the smallest atom to the ultimate fate of the universe, and everything in between. Like it or not, we're all playing the thermodynamic game. We can't win, we can't break even, and there's no way out. Thank you for listening to this episode of Physical Attraction. There are so many things you can do to support the show. One of the nicest ones is going over to www.physicspodcast.com, to the Physical Attraction Facebook page, or to PhysicsPod on Twitter. 3 options there. Any one of those you can use to say, thanks for the show, or give me some advice, give me some feedback. What would you like to hear? If you've got any listener questions, I'm really trying to compile a big list of questions from you guys so that we can do a proper Q&A session, and hopefully I can answer some of the questions that you have about the episodes or about physics in general. And if there's any guests you think I should have on the show, any topics you'd like to talk about, I'm very open to you guys telling me what to do, in a nice way. If you'd like to help us, there's plenty of other things you can do. On that website you will find that we have episodes for sale. You can get an episode for $3 by a donation through Patreon or through the PayPal account. And, this isn't about making me a millionaire. It's about paying for our hosting costs and maybe a tiny bit of recompense for all the books and all the time I spend writing the show. But if you don't want to do that, one of the best things you can do is leaving us reviews on iTunes and telling your friends about the show. Because, in terms of not financially supporting the show, if you tell enough people about it, eventually, presumably, the show will get out to some deranged, aged billionaire. Someone who has nowhere to leave all of their vast diamond fortune to. And, in that case, there's just the off chance that I might wake up one day and PayPal tells me that I no longer need to have a job of any kind. And that would be nice. Then I could probably get 2 episodes out a week. So, until next time, stay safe and look after each other. And try not to break any of the laws of thermodynamics. And if you do, try and get the paper published. See you next time.
Thank you.